When launching the space shuttle on the back of a rocket, NASA scientists must calculate the escape velocity, which we will learn is the derivative of the position function of the rocket. Hi, my name is Tom Atwater, and that's what we will be studying in today's lesson. Let's start by defining instantaneous rate of change. The instantaneous rate of change of f with respect to x at the point A is the derivative. F prime of A is the limit as h approaches 0 of f of A plus h minus f of A, all divided by h, provided that the limit exists. Let's try this out by looking at an example. We want to find the rate of change of the area of a circle with respect to its radius. Evaluate the rate of change of the area A at r equals 5 and r equals 10. And then, if r is measured in inches and area A is measured in square inches, what units would be appropriate for the derivative of A with respect to r? So what we need to do is find the derivative of the area of a circle. So the area of a circle, of course, is equal to pi r squared. Take the derivative. dA with respect to r. And that's going to equal 2, round in front, pi r raised to the 1, because we subtract 1 from the exponent. So now that's our derivative, 2 pi r. In particular, we're interested when r is equal to 5. Then we will get that the derivative is equal to 10 pi. And we're also interested in when the radius is 10. So the derivative with respect to r will be 20 pi. Now, the other question it asked us is, what would be the appropriate units of measurement for dA with respect to dr? And remember that area is in square inches and radius is inches. So the appropriate units of measurement are square inches, with represented by the area, divided by inches as represented with the radius. Next, what we're going to do is look at motion along a straight line. Suppose an object is moving along a straight line so that we know that its position as a function of time is going to be s equals f of t. The displacement over the interval of time in question is going to, that is from t to t plus delta t, that's our interval. Then that displacement is delta s equals f of t plus delta t minus f of t. And then the average velocity over that same time interval is equal to delta s over delta t, which then is equal to f of t plus delta t minus f of t, all divided by delta t. To find the object's velocity at an exact instant t, we need to find the limit of the average velocity as we let delta t shrink to 0. Well, of course, that's the derivative. All right, so now what we'll do is define instantaneous velocity. The instantaneous velocity is the derivative of the position function s of t with respect to time. At time t, the velocity is v of t equals ds dt, which equals the limit as delta t goes to 0 of f of t plus delta t minus f of t, all divided by delta t. So let's do an example of where we apply that theorem, or that definition. The position of a particle moving along a straight line at any time t greater than or equal to 0 is s of t equals t squared minus 3t plus 2. A, find the displacement during the first 5 seconds. B, find the average velocity during the first 5 seconds. And C, find the instantaneous velocity when t is equal to 4. So what we need to do first is find the displacement over the first 5 seconds. So what we have is to take s of 5 minus s of 0. So that would represent the first 5 seconds, t being measured in seconds, and now our displacement, s, is being measured in meters. So we need to plug that into our original function. So this is going to equal, plugging in 5 squared, which is 25, minus 3 times 5, so minus 15, and then we have the plus 2. So that's just s of 5. Now we have to subtract off, plugging in 0. Well, of course, 0 plugged into x squared is 0, and then 3 times 0 is 0. So we're just going to have the 2 as the constant that's left. When we simplify that, we will see that it's equal to 10. And as I said, it's meters. Now, part B was to find the average velocity. Well, we know that we went, and remember, average velocity is equal to the displacement, 10 meters, divided by the time, which in this case is 5 seconds. So it's 10 divided by 5. And so the average velocity will be equal to 2 meters per second. And the third thing, or part C, that we were supposed to find was the velocity, which of course is the first derivative of the displacement. And we can do that s prime of t, and remembering that the original function was t squared minus 3t plus 2, so the derivative is 2t minus 3. And we want the instantaneous velocity when t is equal to 4, so that would be 2 times 4 minus 3, which gives me 5 meters per second. And that would be my instantaneous velocity at time t equals 4. Now, two concepts related to velocity are speed and acceleration. Let's look at their definitions. For the definition of speed, speed is the absolute value of velocity. In other words, the absolute value of ds dt. Acceleration is the derivative of velocity with respect to time. If a body's velocity at time t is equal to v of t equals ds dt, then the body's acceleration at time t is, acceleration is the derivative of velocity, which is the second derivative of displacement, or in other words, s. Let's look back at our last example and add some parts to it. We're going to look at the same particle moving along a straight line and for times greater than or equal to 0, and we'll still use the same function, s of t equals t squared minus 3t plus 2. But this time, we want to, A, find the acceleration of the particle when t equals 4. Then find the values of t, or find what values of t does the particle actually change direction. And then finally, find where is the particle when s is at a minimum. Well, all of these involve the derivative. So starting with A, finding the acceleration, we need to find the second derivative of the displacement s of t. So we know that s was equal to, or is equal to, t squared minus 3t plus 2. We've already calculated s prime, and that was 2t minus 3. And now s double prime, which of course is the acceleration, is going to be equal to 2. It's the constant 2. So regardless of the time that we're interested in, it was specifically t equals 4, we have an acceleration of 2 meters per second, or in other words, second squared. Now, the next part is change of direction. And for the change of direction, that happens when the velocity is equal to 0. And remember that the velocity is the first derivative, right? V of t is equal to the first derivative of the displacement. So we set that equal to 0. And then down here, we'll solve it and see that 2t equals 3 and t equals 3/2. So that's when it will change direction. Now, for the last part, which was to find out when s was at a minimum, well, that too happens when the velocity is equal to 0. It happens when t is equal to 3/2. And when that happens, we take the 3/2 and plug it back into the original equation, and what we'll find is that s is equal to negative 1/4. So that's how we can use the first and second derivatives along with the original displacement to find velocity and acceleration. Now, economists have a specialized vocabulary for rates of change and derivatives. They use the word marginals. Let's take a look at an example from a business world. Suppose it costs our c of x equals x cubed minus 6x squared plus 15x dollars to produce x radiators when 8 to 10 radiators are produced, and that r of x equals x cubed minus 3x squared plus 12x gives the dollar revenue from selling x radiators. Your shop currently produces 10 radiators per day. Find the marginal cost and the marginal revenue. Well, of course, as I just described to you, marginal means derivative. So we need to take those two equations for the cost and the revenue and take the first derivative. So c prime of x will be 3x squared minus 12x plus 15. And in particular, they asked us to find the marginal cost when we are producing 10 radiators. So we take c prime of 10, and that's going to equal 3 times 10 squared minus 12 times 10 plus 15. And that will equal $195. So that's our marginal cost of producing 10 radiators, $195. Now, what about the revenue? Well, the revenue, we would have to take the first derivative of the function r of x. So r prime of x is going to equal 3x squared minus 6x plus 12. And once again, we have to evaluate that for the 10 radiators. So we plug it in, and that will be 3 times 10 squared minus 6 times 10 plus 12. And that will give us $252 for the marginal revenue. Well, now it's time for you to try a problem. The problem is going to be similar to the one I did. Suppose that the cost of producing X washing machines is given by C of X equals 2,000 plus 100X minus 0.1x squared. I want you, A, find the average cost of producing 100 washing machines, find the marginal cost when 100 washing machines are produced, and show that the marginal cost when 100 washing machines are produced is approximately the cost of producing one more washing machine after the first 100 have been made. Pause the video while you work on this problem, and when you are finished, restart the video to check your solution. All right, let's find out how you did on this. Here's the original problem that I gave you. Let me go to a clean screen so I can work it out. And the first thing we had to find was average cost of 100 machines. That's going to be the cost of 100 machines divided by 100 machines. And that's going to be equal to 2,000 plus 10,000 minus 1,000, all divided by the 100. And when you work that out, that works out to $110. The second part is we have to find the first derivative of the cost function. So the first derivative, C prime of x. Well, of course, remember that the 2,000 would just be a constant, so that's going to be plain old 0. Then we would have that the remainder of it is 100 minus 0.2x, and that's the first derivative. Now, what we're interested in is the marginal cost of the 100th machine. So we want C prime of 100. So that's 100 minus 0.2 times 100. And when you work that out, you get $80. Whoops. Okay, the last part, the cost of producing 101 machines. So that's C of 101. So you have to plug that into the original function. When you do that and work out all the arithmetic, that is equal to $11,079.90. Before we calculated that the cost of the 100 machines is $11,000. So if we subtract off the $11,000, what we'll find is that the cost to produce the 101st machine is $79.90, which is very close to the $80 that we projected by doing the first derivative, i.e. the marginal cost of the original cost function. All right, so in this lesson, we looked at the first derivative and the second derivative for velocity and acceleration. And then we looked at the first derivative for marginal cost and marginal revenue. Be sure to work the exercises that your teacher assigns, and we'll see you next time.